The next speaker, Andrey Sadofyev, who will speak about Zilch, Berry
Okay,
phases, and kinetic theory.
okay. Let's probably turn off the video and so it better. Um, okay. Let's go here. So first of all, I want to thank organizers for the opportunity to talk about our recent work and for this nice workshop. It's definitely exciting time to discuss all this physics. And I will start with congratulating Valentin with his past birthday. Valentin is three-time supervisor of mine. So I did undergrad, master, and PhD thesis with him, my Russian PhD thesis. We had a lot of works together, published in different journals, and from what we discussed during my studies time, many of my later works basically came out of these discussions. So um, in this sense, Valentin really shaped my um, scientific interest and career path. As an anecdote, I should tell nice story. Um, a long time ago, Valentin gave me and our co-author Vladimir Kirillin, who was my group mate from undergrad, a problem to calculate something. It basically was Chiral vertical effect in Chiral superfluid. And in superfluid, you don't have rotation, so it's realized through zero modes on vortices, and we calculated it, and we found that the answer is twice larger than we expected from basically normal Chiral vertical effect in literature. We were confused, so we decided that we wait a little bit. We spent, I think, about months trying to get it right, as we thought right. Then we came to Valentin, we were kind of arguing that probably we did something wrong. We went, he said that us to check what we did. We went out again for months or two to check our calculations, which were quite simple, and it was embarrassing in this sense. And then in some time we came to Valentin and said, okay, finally, we did it in all possible ways, and we got this factor of 2 twice larger than in a normal Chiral vertical effect. We have no idea what to do. We must be somewhere wrong in something. And Valentin said as, oh, you are right, and we should write a paper. So as a takeaway of one of takeaways of my studies under Valentin's guidance is if you calculate something in 10 different ways and you get answer which you don't expect, probably you have problems with the expectations and not with the answer. Okay. Another funny fact which I think Valentin is not aware about, and I will just present it here. A long time ago when I was in grad school at my TV, initiated some yearly event, which is kind of Olympiad in theoretical physics for undergrads, and looking for a design of a web page, we were trying to find a nice work to put formulas in the back of basically in the background, and now it has some sub summary of ABC of instantons, and it's even properly cited in Russian here. So students solving problems in this Olympiad from different fields of theoretical physics actually looking at ABC of instantons. Okay, so here I want to now turn to back to the talk, which also in many different ways follows from our discussions with Valentin and our finished works and our ideas which never were finished and then got new reincarnation in this work. I will give a brief introduction. I will turn to some new Chiral effects for other massless particles, non-fermionic massless particles, and particularly to photons. Then I will talk about Chiral kinetic theory, Wigner functions, and finally I will come to recently suggested Zilch Vortical effect and related physics. So let's go there. Heavy ion collisions, if they are non-central, naturally produce large, fast rotation of matter and large magnetic field just created by the currents of spectators of these leftovers of the original nuclei. And in this rotating matter and matter under strong magnetic fields, one naturally expects polarization of spins. That's on general physics grounds. It's like in Einstein-de-Haas or Barnard effect. So these polarization phenomena are very interesting because of particles at the large temperatures are massless in the system. Basically, we can look at essentially massless quarks and gluons. So when we look at quarks, what will happen in like fastly rotating matter, the spins will get polarized. So since chirality is slaved with momentum, it will also mean that if spin polarized, there is separation of chiralities. Right particles going up, left particles going down. And if you calculate this thing in like, say for free direct fermions in rotating matter, you will find this answer, which was essentially obtained by Valentin in like late 70s, early 80s. Much later in 2000, around 2010, like a little bit before, it was realized that these effects might be connected to anomalies. And there are different arguments why this guy here is connected to the axial anomaly. And then there are discussions why this guy should be connected to gravitational, so let's move this guy here, to gravitational anomaly, which is the thing here. It's called mixed axial gravitational anomaly. And it's a simple thing. If you have massless fermions, direct fermions in gravitational field, axial charge is supposed to be conserved. However, gravitational fields break it the same way as usual electromagnetic fields. That's local mixed gravitational anomaly, and the original suggestion is due to Chiral. However, later there were other suggestions that this effect related to some global anomalies, and again there are more recent works arguing that the proposal by Chiral is correct. So it's still under discussion. In this way, this effect is more or less established. However, there are still questions to the microscopics of this effect, and this effect is under active discussion. And that's how we will go. First, let me try to explain why the Chiral Vortical effect related to axial anomaly. It's first part, this thing. And here I have awesome chance to cite our work with Valentin, which was essentially in the basis of my undergraduate thesis. The idea is following. You take fermions and you write the action for fermions where you introduce chemical potentials. That's the standard way how you can introduce chemical potentials. Okay, you need to do something finer to introduce B5, but it's very natural. Now you can notice that A can be naturally combined with mu's together. Because of A also has gamma, so they come kind of together. Moreover, if you boost your system with constant boost, you introduce some velocity for velocity of the frame. And then it looks like a very natural shift. You just need to reformulate your theory of fermions in a new extended gauge potential. Then, if you additionally allow U to depend on time and space, and you ignore high derivatives corrections to action, what you will find is that the velocity can contribute to the anomaly. That's effective field theory level of discussion. So this is not modification of microscopic anomaly, but modification of anomaly in effective field theory. And in standard way, if you turn the triangle diagram on the side, you will see that the electric currents should be multiplied by mu u, this shift of gauge field. And then you get the axial current, which looks exactly as it should, u squared omega. And you can get also B5 squared omega the same way. This is pretty nice. So you can see at least some relation of Chiral Vortical effect to anomalies in field theory, not only in completely effective approaches like Hydra. But now you can ask what's about this guy. So the problem here is following. The argument that it's related to gravitational anomaly is hard to penetrate because of this thing on the right hand side of d mu j5 mu is of fourth order in derivatives. And if you do Hydra-like calculation, you expect that this thing should contribute to j5 at third order in gradients. However, this guy here is of first order in gradients because of omega has only one derivative, so it's different smallness, if you wish, in Hydra expansion. So it definitely cannot be included in Hydra-like considerations, say like in Son and Surov. So it's interesting to understand the origin of this effect and interesting to understand if, how it's related to anomalies, if at all. The natural idea maybe, the natural idea maybe is apart trying to calculate in field theory, where it's hard, is to look at something. Okay, is to look at this problem from the other side. Let's forget about anomalous nature of this effect and try to just look at it as a polarization effect. So here I rotate my system and I polarize spins. And because of the particles are massless, there is separation of chiralities. What will happen if I took other particles with spin and they are massless? For example, photons. I definitely will have the very same picture, at least at the general, general physics level. So if I have photons, the photons have polarizations, they are massless. They would like to get spin aligned with angular velocity, and I would expect some chirality separation. And in my discussion with Valentin a long time ago, I noticed that in old works, Valentin and co-authors suggested that there is gravitational anomaly for photons. So this can serve as a motivation to study Chiral vortical effect for photons, because of if it's said that this effect related to mixed gravitational anomaly for fermions, and I have other massless particles with gravitational anomaly, I probably can hope to find the same type of, I can hope to find an effect of the same type and with the same relation to the anomaly. With this motivation, we introduced Chiral vortical effect for photons, which indeed follows from simple calculation in Kubo style. We considered response of photon helicity current to medium motion, where TOJ is just like used to simulate medium motion because of the slow varying boost of system to the rest frame of of your, if you wish, fluid or matter can be faked by gravitational field, so it's the appropriate correlator, the appropriate conductivity. And we found that indeed there is this effect, very natural. The coefficient doesn't matter now. T squared is just dimensionality here, and again, along angular velocity where omega mu it's a relativistic generalization called vorticity. So that is Chiral vortical effect of photons. Now, one can ask very natural questions. Is it anomalous? If fermionic effect is anomalous and related to gravitational anomaly, is this one anomalous? Then, apart from discussion in field theory, chiral effects were actively discussed in context of semi-classical description and kinetic theory. Particularly, it was started because of condensed matter applications. Because of condensed matter systems, people solve some similar phenomena, and some of them even were measured. So it's interesting to ask if this chiral vortical effect in case of photons related to some topological phases, as it is the case for fermionic chiral effects. Then, since I just shown that there is this effect for photons, I would expect that there is this effect for any massless particle with spin. And then this current is not ideal choice of observable. One can argue that it's not gauge invariant. However, the good part of this current is that its full charge is gauge invariant. So if you take K0 and integrate over the whole volume, you will find that it's gauge invariant. But it doesn't give you local measure of chirality separation. So one can try to find something better, something what will look more appropriate for experimental applications. Now let's, as I said, we have a good reason to think that it may be related to this anomaly, but more work required. And to avoid doing complicated field theory, let's start with this other question. So the idea here is following. It was originally introduced by Son and Naoki. If one take effective action for massless particles and takes the leading semi-classical correction, the action will look like that. And there will be term which looks like a gauge field in momentum space. You can notice that these terms are very similar. It's just like you kind of exchange x by p. The equations of motion following from this action, there are basically equations of motion for x and p both, because of its already phase space dynamics. You will find that there is something funny. This thing called Berry potential. It's actually not Berry phase, it's Berry gauge potential. Causes something like magnetic field in momentum space. And this magnetic field for massless particles looks like magnetic field of magnetic monopole, but it's like this fictitious magnetic monopole in momentum space, so it's not in X space. However, it affects the dynamics, and if you calculate current of these particles, just counting these particles, saying that you can count the current particle by particle, you will find that there is current magnetic effect, current separation effect, and all others. Moreover, if you do a naive substitution introduced by Misha and Yi in 2012, basically the same year, they use the idea that there is Larmor theorem that you can, in classical mechanics, you can fake effects of Coriolis force by replacing magnetic field in Lorentz force with 2m omega, and just replacing m by the energy of particles. We have now relativistic particles. They found Chiral vortical effect, which exactly agrees with the result from field theory. Okay, so I don't want to talk about anomaly in kinetic theory. It's a more complicated question what it means to have anomaly there. However, all these effects clearly come in the very same way. Chiral magnetic and chiral vortical effects, in this sense, are related to flux of this magnetic field, this very magnetic field in momentum space, which enters like number here, if you wish. Okay, now can we do something like that for photons? We asked this question with my collaborator Shuguang, and what we've and actually it was, yeah, historically it's even better. So originally, soon after our work with Arthur about chiral vortical effect for photons, Naoki Yamamoto realized that kinetic theory can be generalized, and he found pretty curious refs out basically of our field. The refs going back to Zildovich, to 92, and to somebody called Bloch, who basically revived these works by Zildovich in the context of quantum optics. In these works, people were discussing that there can be something like anomalous Hall effect for light. And the idea is following. Light beam can be described by equations very similar to the semi-classical equations for massless ferment. And there is topological phase for light. It's here. It looks like exactly the Berry phase for ferment. It has like a name Berry's, it's not, now people normally call it Berry phase, but there are some other names which can be placed there depending on whom you ask. And effective electric field can be introduced for light, for example, in gravity, so going back to astrophysical cosmological applications, or by optical activity in material in quantum optics, so looking at this work. The idea is very simple. So you prepare some transparent crystal which is active, so it's not in equilibrium. You make a gradient of refractive index, and you will find that depending on polarization, the light will be shifted in two different ways. So light polarization will get tiny kick, like right polarization will get tiny kick up, and left polarization will get tiny kick down. So out of this point, one can immediately expect that there should be that the discussion for chiral effects in kinetic theory should be generalizable to case of photons from ferment, and it was done by Naoki. However, the calculation of vortical effect in kinetic theory relies on this shift of or this separation. On this substitution of magnetic field by omega. With Shuguang in 2019, we wanted to understand how in fact it works, and we tried to find other way to derive chiral kinetic theory in rotating frame. We followed a little bit different path than Misha and Yi did originally, and Naoki reproduced for photons. We tried to introduce semi-classical Hamiltonian for massless particles, where S is what take place of sigma matrices for photons. It's just like appropriate matrix in the right representation of spin. Then this, you can consider Heisenberg equations for this Hamiltonian, and it's known in literature that if you integrate out spin degrees of freedom, you will find semi-classical equations of motion. They look a little bit different from what you can get in other methods. However, in fact, we've shown in our work that the different forms of equations, of phase space equations, in fact, related to coordinate transformation in phase space. Now, if you calculate the current, so you take these equations, you look at x dot, and you notice that energy density depends on x explicitly, so you should take into account magnetization current. You calculate it, and you find the answer, which now depends on spin, so explicitly through overall coefficient, and through what f you put here. And if you calculate it for plugging there spin 1/2, you will get just Chiral vortical effect for ferment. Now, if you plug there s equal 1, you will get some version of Chiral vortical effect for photons. And the only issue, which clearly you can take any other spin. The only issue which is left now is that this current is number current in kinetic theory. While for fermions, it's more or less obvious what happens with this current in field theory. So what object in field theory will give you this current? It's not that obvious for photons. But if you, taking just as a fact that there is this object which counts the different number of right and left photons, you can see that there is general Chiral vortical effect. Okay, so in this way we construct a Chiral kinetic theory for massless particles with any spin. CV is general phenomenon, is apparent from this consideration. So now one can go to field theory and try to see how it works for spin 3/2 or 2, which is a little bit exotic but theoretically interesting. The equation with anomalies is still here because I didn't manage to show anything in field theory. However, now I see that all vortical effects arise together in the very same uniform way. Thus, if I argue that one of Chiral vortical effects, say for fermions, related to some anomaly, the same should be true for others. If this argument robust, if it works, you should be able to see that there are gravitational anomalies for all right observables, for all right chirality currents, and in parallel you can write Chiral vortical effect for all these different guys and relate them. And the relation should be the same. And finally, this Chiral kinetic theory in the case of fermions was used to describe polarization of spins and dynamics of quarks in the QGP phase. So one can try to use this approach and extend those considerations to study polarization of vector particles, of photons and gluons in hot phase, and of vector mesons in cold phase, in hotter phase. Okay. However, we also use this semi-classical approach, which one can call naive kinetic theory. Because of this kinetic theory, rather deduced, not derived. And in our more recent work, we try to overcome this issue and just derive the Chiral kinetic theory from first principles. And it's known that one of best ways to do that is to use the Wigner function. So we constructed Wigner function for photons. Photons are non-interacting, so we ignored corrections to which will enter to collision term. So we'll consider free kinetic equation, and we write the equations of motion for Wigner function. It just solves the same equations of motion as the equations for field. Just you need to be careful because of the points are separated. So you will get this pair of equations, this one Boltzmann-like equation, which already tells you that it will look like kinetic theory, and this one constraining the spectrum. And also because of that, this object is not gauge invariant, you need to fix gauge. So for instance, you can fix gauge being Lorentz gauge. That will give you this equation. Now, it's not the whole story because of there is additional gauge freedom in free photodynamics. So if you have free Maxwell equations, you probably know that column gauge allows you to fix one more component despite that the Lorentz gauge already imposed. And to make it a little bit more general, we introduce constant vector n, which fixes some combination of components of gauge potential to be 0. And if n equals 1, 0, 0, 0, it will be just current gauge. And after that, we solve for Wigner function order by order in semi-classical expression, where h bar enters to this story through this coefficient here, through the separation between different terms. Okay, so at zeroth order, the equations look trivial, and it's very hard to constrain the system. However, yeah, the standard approach to this problem is to use an ansatz motivated by field theory calculation. One can calculate the Wigner function at leading order, so in equilibrium, essentially. And if one does that, it looks just like this thing. So this is projector, which is transversed to momentum and to n simultaneously. So it satisfies the equation that n dot omega dot w and p dot w is 0. And this is something which should become the distribution function later. So now with this ansatz, the procedure is straightforward. One can just derive the W1 out of W0, W2 out of W1, and so on. So writing the equations at the next order for W1, one can find that it's convenient to separate them into symmetric and anti-symmetric parts. And in fact, anti-symmetric part is not interesting for us. It won't contribute to polarization effect, so I won't discuss it anymore. But anti-symmetric part has non-trivial contribution. And if one solves its general form, there is free function in it. Here it's given. So this free function should be fixed somehow. However, it's already good. We fix part of Wigner function and its general form. And this free function here can be partially fixed if one requires gauge invariance of another Wigner function for field strength standards. So if one does a simple exercise plugging this thing into this Wigner function, that's what will happen. The part of u will be fixed with thermal vorticity, and there will be a free function u0, which now not multiplied by anything, by any gauge vector. So this thing is gauge independent, but not fixed. Okay, so then the only thing which can be can be done further is you go and look at some known expectation value of operator and try to understand the meaning of this u0, and then construct either calculate u0 in particular setup, or construct a model where u0 takes the corresponding value. So it's now a parameter function of the description. So Wigner function is constructed, u0 unconstrained. We should compare expectation values, and that's what we will do next. And here I will come back to what Oleg was mentioning, to something called Zilch. Zilch means nothing in English. So Zilch current introduced by Lipkin in the 64 is a conserved current in free Maxwell theory, and Lipkin didn't find use for this object, so he called it Zilch. So essentially nothing. However, later it was realized that Zilch can be useful, and the reason for that is simple. If K0 counts the difference between number of right particles and left particles, Zilch count numbers of between right and left particles, photons, weighted with some power of their energy. So it's still a measure of helicity transport, but this measure is weighted measure. Okay, now in our work in 2017, we introduced this Chiral vortical effect of photons, and later Maxim, Carl, in their work introduced this co-author introduced the same effect for Zilch. So essentially what they considered rotating gas of photons and calculated Zilch current in this case. And this Zilch current has counterpart of CV for photons, and they call it the Zilch Vortical effect, which is pretty natural now. Okay, so yeah, now this Zilch current is not uniquely defined, and there is actually a whole tower of Zilch currents which have more and more indices. So I will call this as spin of Zilch. And there is a nice choice which gives you a little bit more definiteness. The choice is to take symmetric Zilch, which can be introduced like that. So we try to calculate this symmetric Zilch in our case with Wigner function. But first, let's try to think how it will look like in CKT. If one thinks in terms of just single particle polarizations, this Zilch probably should look like something here. So it will have moment, and the only other vector which can have distribution function is J. So in kinetic theory, you expect that Zilch looks like that. And this J is the J which we introduced in kinetic theory, and we don't know how to introduce in field theory for photons. So this J is the number current in kinetic theory. It naturally relates to discussion of side jump in kinetic theory. The idea is very simple. If you write full angular momentum, it has two parts. It has a standard orbital part and spin part. And for massless particles, there is the standard constraint on the spin part is insufficient. So there is no way to fix spin part without putting some other condition into the discussion. So this n is intentionally called n, the same n as my gauge vector, and I will show that it's in fact the same thing. However, here it would be called frame vector. So this vector fixed frame where I want S to be to have particular form. With this extra constraint, I can fix S, and then I will try to ensure that all these are, and goes back to discussion of Son and co-authors. And the current, for example, takes this form. So the n corrections in F and in the n corrections to the distribution function and to the definition of current should compensate each other. And if you properly study this theory, you will find this answer. So the subleasing correction to semi-classical correction to the current looks like that. Now, if you plug it to the definition of Zilch current, just naive definition of something with the right tensorial properties. So with the right number of indices, symmetric, and invariant under the choice of n, you will find this answer. So that's what you expect in kinetic theory. On the other hand, if you take Wigner function and you plug it to the field theoretical definition of the Zilch, you can see that you get exactly the same thing, or at least the same structure. You can see it here. So that's what you get with Wigner function. And that's what you will get in the kinetic theory with J being this thing and S being that. So you can recognize that this structure here, it is just the spin tensor, which appears inside the definition of J. Then simultaneously, you could guess what U is. U is P mu F, where since it's axial object, so the object which involves difference of right and left particles, U is the difference of F for right-handed and left-handed particles. Okay, now if you calculate Zilch, you will see that U0 should be 0, because if we don't have difference between number of right and left-handed photons in equilibrium in this system. And I guess my time is, essentially over. I ran over time like in a couple of minutes. So let's just run through summary. We have constructed an AFCKT for massless particles of arbitrary spin. Then we, looking at the case of photons, we decide that it's not good enough, and we try to derive this kinetic theory. And we indeed managed to derive it using Wigner function for photons. So at least at the level of some observables, this kinetic theory indeed reproduces a naive construction. And there is some interesting thing. In chiral kinetic theory, there is an extra object, which called frame vector. This is a vector which fixes the form of spin tensor. And here we see that this frame vector is exactly the vector fixing residual gauge freedom of photons in the case of photons. So quite curious interplay of freedom in two series. Now, talking about chiral effects, we see that chiral vortical effect is a general phenomenon, and it relates to the Berry phase for all cases. Moreover, there is a whole family of Zilch vortical effects. Here we proven that it exists for photons, that is a whole tower, because of Zilch vortical effect, essentially rise in all Zilchs, in the tower of Zilch. But since kinetic theory is a very, since kinetic theory is very natural, can be naturally generalized to other spins, I would expect that Zilch vortical effect can exist also for other spins. So there is a two-parameter family of vortical effects for massless particles, where one parameter is spin of observable, and the other parameter is the spin of particles. And now these things can be related, since they describe transfer of polarization, one can try to apply new observables to real phenomenology. With Zilch vortical effect, it's hard because of Zilch is not conserved on interacting systems. On the other hand, it's known to give reasonable measure of chirality transfer, say, in soft condensed matter. So it will be curious to see what happens in heavy ions. And finally, some questions for future. The family of vortical effects is there. I shown you that some of these effects, that the conceptually, the logic that vortical effects related, the thermal part of vortical effects related to gravitational anomalies can be extended because of there is gravitational anomaly for photons. But can one show it to be correct and show it for all spins altogether and better in field theory? Then one can construct Wigner function for photons, but can one extend it to massive particles because of there are already first measurements for polarization of massive vector particles in Kavanaugh experiments. Then, with this discussion of kinetic equation for spin one particles, one can wonder if writing hydrodynamics with spin based on different Boltzmann-like equations useful to constrain its form, because of at the hydrodynamic level, it shouldn't matter what particles enter there. On the other hand, at kinetic theory level, it definitely matters. And one can go further and ask whether there are gauge invariant measures of polarization in interacting systems. Because of Zilch current conserves only in non-interacting systems, and it's some pretty not real question. Okay, so I probably should stop here.
Okay, thank you very much, Andrey, for interesting talk. We are just a bit behind the schedule, so,
Yes.
but only, please, only short questions. Nukhzar, do you have short question?
Yes. We have seen that spin particles, including high spin particle, has some characteristic dynamics. How we can detect what are the signatures of high spin particles, if there are any?
So we should, I guess we should start other way around. So higher spin particles here would mean, like, for example, to look at polarization of photons or gluons in heavy ion collisions. So you don't need to go to some more exotic mathematical discussions. By higher spins, I rather mean 1, 3/2, and 2.
Not that.
So yeah, so the straightforward phenomenological question whether we can see polarization of photons in heavy ion collisions.
Denis, do you have?
Thanks for the great talk. I about the relation between the Chiral vortical effect and the gravitational anomaly. On one hand, the Chiral vortical effect is related to the rotation global, and there is a derivation, for example, in Son's paper from the gravitational anomaly, but the gravitational anomaly Riemann tensor, and namely one should think that change of the reference there cannot emerge, or it is due to the finite temperature effects that
first
anomaly, because namely
I didn't hear part of your question, but I guess I know what you're talking about, but there is
probably there is no curvature in rotating system.
Yes, sure, but there are no electromagnetic fields in a rotating system. Why is this guy here related to actual anomaly which disappears in the absence of E dot B? So it's the same question. There is some non-trivial intrinsic relation of different relational functions in field theory. Some of them involve stress energy tensors, some don't. So it's more non-trivial than like you have electromagnetic or gravitational interactions which cause some current. It's a relation of current point functions involving TMNU with anomalous point like 3-point function.
Maybe one can add that well, this is the appearance of curvature in divergence, but the current is a surface term, and this is one of the derivations. So this is difference between bulk and surface in a sense.
It's not even surface term. Yeah, you can write, for example,
to derive from anomaly. It's derivation, but maybe we will have time to discuss it. Also, we are waiting for the talk of Valentin Ivanovich, and we will also discuss it. So maybe just we are really a bit behind. So let us thank the speaker again.